Sorry? Okay. Welcome to Accelerate 2025. Let's start off by talking about a little bit of history. Just a second. Oh, gotcha. Thanks. Thank you. Okay. So in 1928, Alexander Fleming discovered penicillin. And in 1952, we have Donald Stuckey. Oh, okay. Looks like we may need to go with. Okay, a second. Okay. So then we also had Donald Stuckey, who discovered a thermal shock resistant ceramic glass. We have Stephanie Kwolek, who discovered Kevlar while studying nylon. Now, materials are discovered through a variety of different methods. We have sometimes mistakes, patience, serendipity, attention to detail, unsafe practices. With Sweet and Low, so who knows about the artificial sweetener, Sweet and Low? There was a scientist that was eating lunch, and he had this sandwich, and he tasted this sweet sensation on his fingertips. And so he rushed back into the laboratory and started taste testing all these vials of tar-based substances until he found the one that produced that sensation. That's how we got Sweet and Low. Definitely don't do that. I want to talk about how historically we've discovered materials, but now we need even better materials. We look at a recent example. We have the world's brightest molecule that was discovered at the Acceleration Consortium in collaboration between University of Toronto, we have Glasgow, we had Vancouver, all together, and 500 molecules were synthesized here. And of those, 10 were the best performing, and this is compared to manually running 10 molecules in 3 years or 40 molecules in 1 year. There are some other examples here. So in addition to the world's brightest molecule, we also have stronger, more sustainable concrete discovered by Meta and used in their data centers. On the right, we have the world's best shock absorber, the geometry of shock absorption. And this one, if you can imagine, the military or bicycle helmet manufacturers are very interested in this kind of application. Now, if we look at the kind of these two fundamental concepts, we have AI and we have automation. Just going to step over here. So with AI, the primary goal is to maximize the value of each individual experiment. So this often looks like reducing the number of required experiments, choosing experiments with the most information gain, and almost always we're ending up predicting properties and quantifying them certain. Now, automation, on the other hand, is all about reducing the burden of each experiment. So this looks like reducing the number of tedious manual steps, increasing our reliability, our repeatability, as well as our speed and our throughput. A self-driving lab, or an SDL, as it's colloquially called, closes this loop of scientific discovery through design, make, test cycles. So first, we initialize our campaign, our scientific research objectives. Okay, I'll speak up. Can you hear me in the back? Thumbs up? Okay, yeah. Cool. So first, we start out with initializing the campaign. Usually this is doing literature searches, having discussions with colleagues, aggregating data. Next, we have the design phase, designing experiments. This is where one acquires a new suggestion for the next experiment to run. And in the make step, this is all your mixing, your stirring. This is controlling your composition and your processing parameters for whatever material that you're making. And then in our test phase, this is where you're measuring some performance property. And so this could be like binding affinity of a molecule focused on drug discovery, or this could be tensile strength if you're optimizing an aluminum alloy, for example. And we repeat that loop until we reach some stopping condition. Now, this could be that your budget was exhausted or your student graduated from their PhD program. It could also be that you've met your performance requirements there. Okay. Now, fully self-driving labs are ones that are able to perform many iterations without human intervention. So if we look along the vertical column, we have at the top human ideation, going to single iterations being suggested, multiple iterations, and generative models. On the top, the horizontal bar, we have automation, and going from manual up to full lab automated workflows. Now, we can think about this in the same way we think about self-driving cars. And as a community, we're really pushing towards these level 4 self-driving laboratories. and having those be democratized and more standardized. So able to automate complete workflows and having closed loop experimentation with suggestions from AI algorithm. Another way you can look at this is to divide up a workflow into multiple categories. So let's say we have synthesis, characterization, sample transfer, experiment planning, and then we'll represent manual intervention with this X emoji. And so at the very bottom, fully manual, you have all X's. And at the top, fully autonomous, you'd have, synthesis, characterization, sample transfer, experiment planning, which would be like orchestrating your workflow as well as suggesting the next experiment. All those things autonomous. So you can think of this in a different way than just AI and automation. Now let's take a look at some of the different types of self-driving labs we might come across. We have these lateral moving robotic arms, picking vials up, unscrewing them, doing liquid dispensing. In this one, we have a inline flow characterization cell. So we're doing inline measurements. We get up to full 6-axis robotic arms. And in this next one, try to count the number of tubes that you see. And there's nothing's moving except for the liquid through various tubes. And then we get to this idea of a mobile robot chemist that can navigate a laboratory environment. My favorite example, perhaps, would be from the Cooper Group in the UK. We have a dual-armed robot uncapping vials and then passing them off to a robot on wheels, which then takes it over to an X-ray diffraction machine for characterization. This is highly sped up, by the way. We get to our XRD machine, calibrate, open one door, open the next door. We need to calibrate again our position, grab our samples, load them in, and lest we forget, we must close the doors as well. So we'll calibrate, close one door, close the next door, and allow the experiment to carry on. Now, when you see this can be a little bit daunting. Who here has ever been off of a high dive before, by show of hands? Okay, we have a few, maybe 30, 40% of you. Maybe you opt to go to a swimming pool to really get this feeling. It can be pretty daunting at first. And this presentation is meant to help you learn the vocabulary and the concepts associated with self-driving labs to avoid this sort of all or nothing thinking of fully manual, fully autonomous. And we're also going to talk about some of the community resources that are available for this. So you want to build a self-driving lab. All right. Can you hear me okay now? All right, thanks. First, we're going to talk about AI. This is all, again, about maximizing the value of individual experiments. Next, we'll talk about automation, minimizing the burden. And third, really focusing on integration. So first, AI. With this, we're mainly focused on the initialize and the design cycles for those phases. And if we look at the history of kind of data and scientific method, we start out with empirical measurements. And we, in the 1600s, began moving on to more theory-driven measurements. So this is scientific laws like Newton's 3 laws of motion. Then in the 1950s, we started introducing physics-based simulations that were really enabled by the digital age of computing. And in the 2000s, we started having these massive data sets that we built models for and started ingesting there. So this would be like the Human Genome Project or AlphaFold. Now, the future of science is increasingly becoming, let's see if this is still on. Okay. It is increasingly becoming autonomous, generative, and agentic. So back here, you remember this slide. Let's talk about these three aspects. We have reducing the number of required experiments, choosing experiments with the most information gain, and predicting properties, quantifying uncertainty. So let's go back to this example with stronger, more sustainable concrete. Here you can see where 6 iterations were performed over the course of 6 months. Each one of these experiments took a very laborious, 28 days for each cycle. And you can see the first batch, this was human ideation. You could say it's kind of seeding or initializing the campaign. And then we have the the subsequent batches that were informed by Bayesian optimization. Meta very carefully worked with the University of Illinois and Amrise, the main company that would be helping them with their concrete in their data centers. And they worked together to build in domain knowledge about the task into their optimization algorithm. And this paid off. They laid this concrete down at their data centers. And this was pretty impressive to me to see it go from, bare ground testing all the way up to, the real impact of reducing the carbon emissions there. Now, this quote comes from Citrine Informatics, a materials informatics consulting company. And they say, not all experiments are equally useful. Some provide more information than others. So this is a diagram called this is a cartoon called the streetlight effect. And we have this police officer and he asks, okay, is this where you lost your wallet? And the person replies, no, I lost it in the park, but this is where the light is. We have this tendency to exploit or really focus in on where the light is, the known, fine-tuning things that we think or have measured to be successful, compared with exploring what's very uncertain. So I mentioned one of those points, oftentimes maximizing the value of an experiment through AI comes with predicting our properties or the mean or average response, as well as quantifying the uncertainty in our predictions. In this next part, we're going to talk and kind of run through some of the classical ways that we've approached machine learning and artificial intelligence and show how some of those can be brought together. When you're working with one of these search spaces in a materials discovery problem, there are many different ways that you can represent your material. So in the case of, we'll say molecules, in this case, we can have a text-based representation, a graph-based one. We can have different physical descriptors that describe it, so-called fingerprints of these materials. And if we look at reactions, we could also have a text-based format or a graph-based format for said reactions. Now, classically, we've had many machine learning models, such as random forest or neural networks. Perhaps you've heard of those. Now, these are fundamentally about predicting properties and using some very basic math. This is a decision tree on the left here that essentially you have these binary splits of some parameter in your search space being greater than or less than some number. And you take all of your data points and you filter them through. And then when you have a new data point, you take it, filter it through, and then take the average of whatever bin it ended with. That's how random forest operates. Now, neural networks, on the other hand, are all about tuning and optimizing the weights of these neurons. It very, very loosely mimics the way the brain, you have neurons firing and kind of strength of certain pathways there. And so similarly, we have inputs on the left, outputs on the right, and we build these rather large networks of neurons or neural networks. We move on to where some of these models have then been integrated into physics-based simulations to speed them up. So here we have this local atomic environment, sort of the shaded region with different atoms there, and we have a potential energy surface. And a lot of pretty amazing work has been done to find general purpose or these generalized models to describe how the local atomic interfaces correspond with the potential energy surface. And so this allows you to speed up some of these physics-based computations dramatically. Now, large language models, these have really been explored recently in the context of materials discovery, primarily through, we'll say, literature, property prediction, and agentic workflows. Now, let's take a look at a tool from Future House. We have these large language models that are steeped in the literature, and we'll take a look at how that works. So here you can see we're asking a question. Has anyone developed an autonomous system for discovering additively manufactured aluminum alloys for structural and aerospace applications. It'll queue that in the system. Wait maybe half a minute or so, and we find these peer-reviewed and non-hallucinated articles that correspond to these these questions that we have. So these different agent-based or kind of autonomous decision-making workflows can call tools and leverage the information, get more context from these tools to be able to rapidly find what you need. I almost exclusively use large language models to reduce the number of keystrokes that I have to make to get to the same level of quality. And there's also a lot of exploration in kind of replacing decision making as well. Then we step into generative models. Now these, in the context of materials, are primarily to allow us to somehow tackle or grasp this idea of chemical white space. On the left here, you can see PubChem, the PubChem database. We have about 1 billion different molecules in that database, and we perform they've performed principal component analysis to do some dimensionality reduction to just 2 dimensions, and you can see the color corresponding to percentage of ring atoms in the molecules. But how do we search through 1 billion molecules in with a machine learning algorithm? It requires a finite number of dimensions to be able to predict that. Similarly, we look at the entire periodic table, or at least those which are easily incorporated into, say, an alloy as our search space. How do we approach that? Generative models really shine there. And they primarily, one of the main challenges we have is the synthesizability aspect. So let's say we have a generative model and we're able to reduce this to some representation that encodes, we can kind of reversibly go from molecule or crystal structure, protein, to representation, and then search around in that representation and go back to what we had originally. There are 2 key issues that we might have. One, does this even exist? Is this even a thermodynamically possible state of matter? And second, let's say it is, what's the recipe to get it? These are some of the outstanding challenges there with generative models. Now, optimization is really at the heart of self-driving labs. And for these, the reason why Bayesian optimization in particular, a type of adaptive experimentation is often used, is because it excels in the low data regime and in a relatively high number of dimensions. So you can see a comparison between traditional design of experiments and Bayesian optimization for a problem that has 6 continuous variables, x1 through x6. And as soon as the Bayesian optimization algorithm is done with its sort of initial exploration phase and goes into model-based learning, it very quickly reaches the minimum compared to these other tools. And so optimization problems, you could think of, find the synthesis pathway for maximizing the binding affinity. You could also look at, say, taking the composition and processing parameters of an alloy to maximize yield strength, for example. Now, I'll often get the question, so there's lots of different optimization algorithms. We have genetic algorithms and all these nature-inspired designs. How do those compare to Bayesian optimization? And if we take a look here, in the blue is Bayesian optimization, and the green is a genetic algorithm. And on the left, we see it as a function of number of iterations. How many individual points did you add back into the model? And on the right, we have sort of cumulative runtime or wall time. So this incorporates the time it took the algorithm to spit out the suggestion for the next experiment. Now, if the, in this case, simulation takes 1 second, we look at the wall time, and genetic algorithms sharply outperform Bayesian optimization. However, if we move the simulation up to 10 seconds or 1 minute or 10 minutes, we quickly see that Bayesian optimization, that overhead of suggesting the experiment, sharply outweighs kind of the quality of the model predictions that we're getting from it. And so in the end, there's almost no comparison between Bayesian optimization and a genetic algorithm in this case. because we're in the low data regime and because our experiments are very expensive. Now, within Bayesian optimization, we have what's called a surrogate model. Now, this is what's doing our prediction and our uncertainty quantification. So the black points here, those are the data points that we've measured. We have some uncertainty associated with each of those. In the blue, we have our model's predictions, the average response. The blue bands are the standard deviation of those predictions. And in the dotted gray line, we have the model, or the true underlying model. The star shows where the global optimum is. And we're searching over one parameter. So this is a very simplified example. And we have one output that we're trying to maximize in this case. Now, an acquisition function, I mentioned, the design step is where you acquire the next point or the next design. The acquisition function guides how we navigate this exploration, exploitation trade-off. So with this one, we have one called expected improvement that's often used. And you'll notice here, once we've calculated this acquisition function across the whole space, we look at the maximum value of that in red. And if you look back up at the model, you can notice two things. One is that it is not the max point of the blue line, and it's also not the max point of the uncertainty bars. It is a statistical model that incorporates both. You get into these integrations over probability distributions, expectation values, but at its heart, one of the things is it smoothly navigates this trade-off or this balance between exploring what we don't know and exploiting what we do know. And as we add more data points to it, we'll see that the uncertainty is reduced in the space, which naturally lends itself to doing more exploitation. So we're iteratively performing this, adding data in, refitting the model, suggesting our next point, doing the make and the test, designing in this loop, and we get closer and closer to our desired target. And optimization tasks, like the one I showed before, would be vanilla in some sense, but things get much more complex. For example, we have multiple different tasks or sources of information, such as a simulation and a real-world experiment. Almost always, I would say actually always, materials discovery tasks are multi-objective problems where we have multiple competing objectives that we're working with. We also often have a mix of continuous and categorical variables. So these categorical variables create these discontinuities in our space. These are often high dimensional. So in this case, we see an alloy data set with 23 unique elements across the entire data set. So a fairly large search space in that case. And we also end up with these kind of strange constraints that are N choose K, or we talk about chemical parsimony, that typically in an alloy, for example, you won't find more than, say, 6, 7, 8 unique periodic elements within said alloy. We can thank nature for those kind of complex constraints. And if we take a look at some of these different topics, and we say we have single versus multi, kind of vanilla versus more advanced for each of these different topics. On the far left is relatively simple optimization. But once we move to something that's, say, multi-objective and high-dimensional, then we are in the more advanced regime. Now, when you look at implementing this from a programming perspective using a state-of-the-art package, on the far left, we'll see something that's 21 lines to run the kind of bare bones, hello world tutorial for this. Now, if you move to the advanced example, we're seeing about a 3 times increase in the number of lines. Oftentimes the syntax, the way you interact with the application programming interface for this tool differs, and that can be relatively challenging. Now, one tool is called Honigumi. Hone means bone, and gumi means collection of bones. So we have this skeletal framework for quickly creating these advanced optimization scripts or kind of hello world tutorials for it. So in this one, this is a tool that can really help accelerate the adoption of Bayesian optimization in the experimental sciences. I'll run you through an example showing how to use the tool. So on the home page, we have that same sort of selection grid that you could see before. And going down, we see this template of sort of the minimal working example for those conditions. Now, if we become obnoxious and we just turn everything to the far right, that script at the bottom will dynamically update to reflect a self-contained and fully runnable example of all of that. And so we can see the script has gotten much more complex. I've watched as PhD students and undergrads and master's students, postdocs have struggled to come up with this minimal working example over the course of months, sometimes up to 6 months to a year. This can save a lot of effort, a lot of kind of crosstalk with developers to figure out how to run this. There are also a variety of tutorials that are really focused on materials discovery tasks. We have a set of hands-on practical tutorials, as well as these conceptual tutorials about, how do we, what does it mean to be fully Bayesian versus have a more frequentist approach to some of these algorithms? How do we implement a multitask kernel or way of representing our model in our search space? And the future of AI and materials discovery is increasingly looking autonomous, agentic, and human collaborative. During this next part, it's going to get a little bit interactive, so I hope you're ready to meet the person next to you. We have first this question: what is your research problem? We're going to discuss this in groups of 2 to 3, and I'd like you to just briefly introduce yourself. What's your name? What's your institution? What's your classical training? What's your background? And then describe, the what and the so what of your research that you're doing. And we'll do this to kind of set the stage for later, where we will have you talk again and frame your research in optimization language. Frame it as a materials or at least an optimization task. So go ahead and take it away. 1 or 2 people next to you. Talk about this problem. What is your research problem? We'll come back in about 3 minutes. Go ahead. We'll come back together in about 30 seconds. Okay. We'll bring it back together now. And don't worry, you'll have more opportunities during the session to continue the conversation. Thank you. So I do something a little bit strange to some when I do the bring back together group discussion. So you talked with somebody, you talked with your neighbor. I'd like you to share something from the person that talked to you. What was their research problem? Could I get some volunteers to share what their neighbor described to them? Yeah, please.
He is working in drug discovery. He's an experimentalist and then gave the research program in health and automation and algorithms to do data analysis. And they use tools in the lab that are supporting the research activities, but it still is a semi-automated.
Awesome, thanks. Okay, we'll get one more person. Don't mind sharing. Okay, in the far back.
So in our group, it's very interesting, very interdisciplinary. We've got 3 people, one focused on materials with AI and physics. The other one is focused on computational biology with genomics. And myself, I'm more focused on the medicinal chemistry with cell time lab. So very interdisciplinary and very cool.
Thank you. Okay, we're going to come back to this. So keep in mind what your research problem or focus was as we start to delve into the terminology and the concepts behind, in this case, optimization and adaptive experimentation. So on the left, we have traditional design of experiments. We design all of our next experiments at once, and we measure all the outcomes at once without any sort of feedback cycle. On the right, we have adaptive experimentation, where we are able to leverage the information from an outcome in the next design iteratively. And we'll say adaptive experimentation is a more efficient version or alternative to traditional design of experiments. Now, let's talk about this in the context of cookies. So, and we're going to talk about this from an example. I have a friend named Marie, and Marie's husband, Ron, was having some health challenges, but he had to have his cookie and cup of coffee in the morning. And so Marie decided she was going to try to make some healthier cookies. So what did she do? She took the recipe that she started with, and she looked at the sugar content, and week after week, she reduced the sugar content until one day, Ron came back and said, Marie, there's something amuck with these cookies. They're kind of gross. And so what did Marie do then? she went to the previous week's recipe and used that one, and that was Marie's so-called healthy cookie example. Now, my question to you, what category does that fall into? Traditional or adaptive? It was adaptive on the right. So we're going to run through a set of questions, and the main purpose of this is to get you thinking of the optimization language. So what were Marie's objectives in this case? Anybody? Yeah. Okay, low sugar. And she wanted it to be low sugar because it would be healthier. Okay. Yes. So we want to sort of maximize the health or keep some, minimum bound on health and the taste of the cookie. What parameter did she tune? Sugar content. What were the constraints on that parameter? Think bounds. Sorry? Okay, so the cookie was the same size, but we have the sugar, sugar content. What are the lower and upper bounds on the sugar content? I know you can't have negative sugar. It's so sad. And what about the max? What was the upper bound in this sentence? The original recipe, exactly. The parameters plus the constraints on those parameters fully define what we call a search space. And the combination of a materials discovery task is fully defined by its search space and its objectives. So we have our search space, which is parameters and constraints on those parameters. We have our objectives, and that altogether is our optimization task or our materials discovery task. There is a lot more, we could say that is the bare bones representation of it. So now we're going to go back together in our groups, and I'd like to ask you, what is your materials discovery task? Or if you don't necessarily have one, think about an optimization task that corresponds to your research. Think of something where you have a search space with parameters and constraints and objectives that you're trying to optimize or maximize, optimize for in that case. So we'll take a few more minutes again. Feel free to take it away, turn to your neighbor. Talking again. Okay, we'll bring it back together in about 30 seconds. All right. Thanks, everybody. In these types of discussions, there's always a peak and then a shift off, and it's hard to find that point. I think I found the right lull this time, so thanks. It says, same question. You talked with somebody. What's something that stuck out to you from there? What was their optimization task? In the back, yeah.
And this here was trying to optimize battery materials for battery. So the objective was or is the capacitance of the overall capacity of the battery.
Okay.
And the search phase is the selection of the materials and the spatial range of the material.
Okay. And it's okay if you pass the mic for this one, but what are some examples of some of the materials? What were the and what were the constraints on some of those? You don't have to go into great detail, but yeah.
We can. In the the user phase.
Yeah, I gotcha. Yeah. So you get into combinatorial problems a bit there. Okay. Yeah. Okay. Thank you. Anyone else? Right here.
So here, the problem is actually quite abstract, that my friends here were sharing with me, and one of them had to do with, if you have a catalyst, like a homogeneous organic molecule catalyst, how can you find other reactions that you don't know that they can promote some kind of lytic activity to, right? So their search space is quite big, which involves many different type of organic chemistry reactions. And I guess like the objective can be how to balance between like exploring and exploiting when you find something good.
Yeah. So looking for different reactions essentially. So that's that's a little bit more of a free form discovery task in some sense. You don't have maximize the catalytic activity necessarily, but you're looking. So I guess a question would be: are you changing the reaction so that you can find something with the highest catalytic activity, or is it more from trying to understand the mechanisms of?
I think what I understood correctly from what they shared, like discovering and like what like this catalyst is good for this, can it be good for other things that we are not.
Okay.
And how to explore that space and do.
Okay. Right. Okay. One more. Oh, yeah.
Yeah, it was kind of a little bit different from my materials discovery task, but Rody here is looking at trying to get to simulate experiments using kind of the simulated robotics almost. So instead of it being like materials and composition, it was more about how you robot get it to most efficiently, which was quite interesting.
Yeah.
So that type of things.
So parameter wise, number of robots to perform a task, constraints on those. Constraints on that parameter, I guess. What would that be?
Maybe like physical layout and all the robots together.
Yeah, I gotcha. And then what's the performance? What's the objective you're trying to optimize for?
Right.
Great. Yeah, thank you. Okay. All right. So that's materials discovery, or at least optimization. I encourage you to continue that conversation when you're meeting with other researchers during the course of this event. You can ask them, like, okay, what's your search space? What are the parameters that you're tuning? What are the constraints on those parameters? What are the performance properties you're most interested in? Those are some things that can really help you quantify those problems. Now, something I like to do when I'm asking somebody what their research problem is or their kind of optimization task, I'll say, like, okay, let's say I want to do it and I'm starting out with a fresh lab. What do I need in there? What's my shopping list? And I say, okay, I have everything there, it's now ordered, procured, installed. What's the first step in my workflow? And you can go on for about an hour with this conversation of, okay, what's the step after that? What's the step after that? And you can get this sort of complete shopping list of what you need to reproduce and this complete workflow. And I find it pretty interesting to learn about people's problems in that way. And you can really drill down what were the parameters, what are the constraints, what are the objectives they're interested in. So that was AI. We talked about maximizing the value of experiments. We talked about a little bit about traditional machine learning, large language models, generative models, a lot about optimization. And next, we're going to focus on the automation piece, which is about minimizing the burden of each individual experiment. And this primarily focuses on the make and the test phases within this self-driving lab loop. Let's take a look at an example. Here we have automation used in organic small molecule discovery. First, a sample preparation step. Here we have a liquid handler at the top left, a stirring and shaking module at the bottom left, a robotic arm for doing transfer at the top right, a solid dosing station, and this vision unit that's on a track. And so you can kind of go through and view these reactions at lots of different vials kind of in line with each other and looking at those individual vials. Next, we get into the throughput synthesis platform, the acceleration consortium and a heater shaker module. And then we get into workup. So we have a high pressure liquid chromatography machine. We have the mass tracking, kind of checking masses in between things. Again, a robotic arm, another liquid handler, and then other things you could go into isolation of a particular molecule and repeating these steps throughout. Now, within automation, you'll find lots of different extremes. In one case, you'll have this buy versus build mentality. So you can go with a platform that's all in one, batteries included. You could have on the far right something fully custom. You're 3D printing and machining everything, writing all of the logic that goes into the devices, writing your own interfaces for using them. And then something kind of in between where you take devices and you integrate them. We're going to talk about some of the different, some of these other trade-offs, and then later we'll go into one of these modular workflows in terms of like this modular integration of devices. So we're going to run into a number of challenges when building a self-driving lab. One will be our research outputs versus our service and infrastructure, our building. Another one will be the time it takes to reach our deliverable and our documentation along the way for the process. Tailored solutions versus aligning with the universal conventions in the community. The level of autonomy, so we go for something fully autonomous, where do we incorporate manual human intervention? Equipment cost versus research fidelity, as well as whether we go with open source hardware and software versus proprietary and often closed source software. And we can find some pretty unique examples where it's both open source and it's commercial and done in a nice way there. So it doesn't have to be one or the other explicitly. I'll talk through a couple different maybe wild concepts as well. Hopefully keep you on your toes as you're thinking about a self-driving lab. One would be the idea of a vertical laboratory. So let's take a kind of this basic synthesis workflow. We have a dispensing unit for powders. We have something where we're doing the synthesis, an X-ray fluorescence machine for doing characterization, and a nano indenter to measure the hardness of the material for our performance measurement. Now, in the traditional lab setting, you have usually a benchtop, and you put some equipment on there, and you might have these larger standalone devices sitting next to it. And as you saw in some of the videos before, you can have a mobile manipulator, a robot arm on wheels to navigate to these different modules. In a vertical lab, you flip that concept, and instead you have the equipment brought to the operator. And so you have some kind of bay or operation table, storage in the front and storage in the back, and a lift or elevator in the middle. And you take your tray of equipment that stays powered on and bring it back into a storage position and bring it back to the operation table. In this case, you would have your experiments, or at least the devices, able to run 24/7. And you could be running experiments with this equipment stored on, basically on shelves and storage there. Now, why wouldn't you get like a robotic arm that can just go up and down? It's because we still need often people to be able to use the equipment and to perform maintenance. And so this is kind of flipping the, always operator to the equipment to the operator. This is one of the ways we can think about designing around workflows rather than just trying to replicate always what a human would do in said workflow. So with this one, I want you to talk about the hardest step in your workflow to automate. Now, this could be software or hardware, but what are the difficulties? What are the challenges in your workflows? We'll say in that optimization task that we just laid out. What's tough about it? So this one, we're going to do a little bit shorter, about 2 minutes. So if you could try to keep it brief, 2 to 3 minutes for this one, but go ahead and we'll bring it back together for some discussion. We'll bring it back together in about 30 seconds. All right, thanks everybody. So this one will be a little easier. I won't force you to share what someone else said. What did you guys talk about? What were the difficult pieces to automate, either in your workflows or somebody that you talked to? Okay, yeah, first here and then here.
I think what we were kind of talking about was that there's some equipment that kind of needs a lot of human interaction to push buttons and drag and drop, and it's kind of difficult to automate that when it's like another company, you don't really have access to put something in there to do that for us.
Never underestimate the pain of a manual GUI when it comes to building a software lab. Thanks. We had somebody here and then another. Yeah, go.
So I think in both cases, like mine, also those I talked to, was that the integration, the use of AI models to integrate in the process to really actually solve the task that we wanted to solve, that this is the actual difficulty. So we have all hope that the AI models have great capacity, but then actually to run it in the workflow and then it really is reliable and robust to do exactly what we want it to do. This is a very big challenge.
All of the validation once you've actually maybe chosen a model and you're trying to use it. And okay, thanks. Yeah. Okay, we had another hand. I think up. Yeah.
Yes, we discussed a little bit in the context of like synthesis. I think they are quite challenging to multi-step synthesis and then connect with this isolation. Because depending on the molecule, depending on reaction, the challenges can be quite diverse.
One pot or one step synthesis with a low hanging fruit. You see many papers, self-driving labs or just automation in general. The multi-step reactions get very difficult. Thanks for sharing. Yeah. So Larry, just up here a little bit.
Yes, I think we're both kind of running into a similar sort of issue working with some inorganic and stuff. So I think that the best way to put it would be that it's very easy to make a mess automatically, but cleaning it up and extracting with one. I would think it's cases where powders, in my case, were with single crystals, actually extracting the target there. So a single crystal getting the powder at certain doses. Challenges to doing that where it's very much sort of a finicky process. That you need to be fast, where it's just with powders. That's what we're running.
Thanks for sharing. This connects a bit back to, I think, the this AI piece and validating it. What I showed you with the search spaces, it's so clean. You can just change any number and you probably get something semi-reasonable. But what you don't see in many of these papers is the behind the scenes where they ran on a particular search space and then turned out this liquid crystallized, and so then it stopped the flow, and so they couldn't actually measure the outcome for it. And there are ways to handle failed experiments and sort of feasibility constraints on a search space. So these are, again, more advanced topics, but I think it's that behind the scenes, hard to automate steps where it's difficult to have it be clean because it gets messy. Yeah. And thanks. Anyone else like to share? See, I'm just curious about what your hardest automation problems are too. So, okay, one more and then we can go.
For us, it's definitely still synthesis. For example, we work with carbon nanotubes. Synthesis involves mixing with polymers and sonicating and centrifuge. So there's a lot of different steps, different machines, different labs to get into. I don't know where to start.
Yeah. Thanks. So by a show of hands, who here has physical science classical training? Okay. So probably about 70%. Who has a computer science classical training background? Okay, maybe 10% of the people here. Who has a mechanical or electrical or chemical engineering background, classical training? So maybe about half. So with the part of the reason I asked this is I was meeting with a mechanical engineering department, and I talked about sort of what might be most difficult, kind of the more difficult aspects. And I kind of had this naive assumption that, almost always it's sample transfer, getting samples from point A to point B in more arbitrary ways. And they kind of came back and said, to us, that's one of the easier things. It's all this software, it's the writing of Python scripts, it's the AI algorithms. Those are the challenging pieces for us, not kind of sample transfer. So depending on the blend of expertise of the person you're talking to, the difficulty can vary dramatically. And so this later in the integration section, we'll talk about some of the resources available to kind of learn these cross-disciplinary skills, or at the very least, learn the vocabulary and concepts for these cross-disciplinary skills that are needed so you can work in a team that's highly interdisciplinary. Okay, anyone else before we move on? Oh, yes. Yeah, please, go ahead.
Yeah, just the cleanup and like ordering things, cleaning them up and following safety regulations. That's probably like one of the hardest combined.
Yeah, the greatest fraction of time and frustration, perhaps. In the brightest molecule example, with that one, when you talk to the scientists who are involved in it, there came this point where shipping the samples across continents became one of the biggest bottlenecks in their workflows. And so, yeah, shipping labels even can get a bit hairy. Okay, anyone else before we move on? Okay. So we're going to go through a couple more of these concepts in greater detail. On the far left, we have these integrated, very purposeful single application systems so you can think of like a chip in your computer. It has a very defined purpose. On the far right, manual tasks and going with something that's more like mobile manipulation that mimic the human. And in the middle, we get into modularity, kind of more flexible solutions, and configurable. Let's go through a couple examples here. So with this one, we have that flow, this inline flow characterization for nanoparticle synthesis. And in this one, you can see we've got these high pressure components that are mixing liquids and bringing them through this particular spectrometer. This would be more on the integrated level, integration, fit to purpose. Now, this one you saw at the beginning, this would be much more general purpose on the flexible and kind of emulating human workflows. Now, something in the middle, we can see a more hybrid setup with standalone modules connected by robotic arms. And this one evolved from the Burlingame lab in Vancouver from 2018 to 2024. And we can see how they began reconfiguring their system, adding additional modules and moving from one application to the next. So on the far left, they were focused on solar cells. In the middle, electrocatalysis. And on the right, more on gas diffusion electrodes, also catalysis or catalysts for carbon capture. We take a look at some of the equipment here. We have on the bottom left this test cell, a 6-axis robot with slide storage. At the top, a spray coater, a characterization robot. Let's start out looking at this robot with the slide storage. So we're picking up a vial. just moving it to a vial decapping station. Next, with the characterization robot, you can see this module as well, bringing a slide down, dropping a liquid onto it, or a droplet. Here we have the spray coater for one of those same slides. So the slide, this is moving all around. And finally, this automated test cell. So as you're designing or building a lab like this, it's important to take a holistic view of it. You not just think about your immediate objectives, but how you intend to have this platform evolve over time. And you can definitely take your skill sets, your interests, and the current opportunities around you into context for that. I'm also going to talk about how this can be more accessible than it might appear. We have, so I worked with Stanley to do a review article, and we really focused on this frugal twin concept, which is like a digital twin, but where it's a low-cost counterpart to a high-cost entity instead of a digital version of something that's physical. And this can be really useful for education, for prototyping, and even multi-fidelity research. We can think of frugal twins as being on a spectrum with cost on one axis and the research fidelity on another. So at the top right, we have a more traditional off-the-shelf commercial research grade system. On the far left, we get into toy examples where we're just mixing colors, for example. And then somewhere in the middle, we get into these lower cost components that can still give us proxies or lower fidelity measurements of our kind of high cost objectives. And saying it's frugal doesn't mean that it's non-performant necessarily either. This is a system that was built at the Acceleration Consortium. Nis Fisker came from Denmark, and he spent about 3 months and for under $5,000, worked very hard to create this system, which was highly research performant. So we have reactor cleaning that was happening. In the next step, we'll see dispensing these metal precursors into one of the wells. We use the same liquid handler to pick up the electrode to do electrode deposition, to clean it using ultrasonic cleaning, and then carry out that workflow in loops. And he did that in 3 months, of course, with a team working with some other people, but it was a big lift on his part. And this is what really impressed me. He went back to his home institution and very quickly replicated the entire setup because he had documented it, because he had built it from components that could be sourced and easily replicated. So a lot of times people talk about reproducibility. I like to talk about replicability. How easy is it to replicate your system in another context? I mentioned a little bit about focusing on the workflow rather than trying to emulate how a person does it. So I call this hardware-centric design. Let's take liquid mixing as an example. So we have a human-in-the-loop version. You have a syringe tip. You're maybe just wiping a needle off. You could get a robot arm to do the same exact thing. Or maybe you could take a needle on a gantry system that can go in X, Y, Z, and helically drill it into a sponge that's fixed, and then bring it back. From a physics perspective, from a reference frame point of view, the needle sees pretty similar forces in that case. So that's an example of hardware-centric design. So Benji was in here a little bit ago. I'm not sure if he's still here. Anyway, so that was a great example there. We could also take this example of liquid mixing. So pouring one vial into another, from one beaker to another beaker, and having a stir plate with a stir bar inside of it. So you could do the same exact thing. Robot arm picks up the beaker, pours it in, and you have a regular stir bar there. Or let's say you have a pump that's bidirectional, and you rapidly agitate the liquid by going one way and the other way. So you get sort of two birds with one stone, so to speak. You're able to bring in liquid, bring out liquid, and maybe get some proxy for a stir bar in terms of agitating the liquid. So those were some of the principles behind automation. We talked about flexibility versus being a very fixed and integrated system. We talked about some of the middle paths and also talked about some of the common pitfalls with that. Thank you for sharing some of your automation challenges as well. I encourage you during the conference to talk with people. What are the things they're most interested in automating? What are some of their biggest challenges? And I think that can really help us figure out what resources are around and get to know each other a little better. In this next one, we're going to talk about integration, and this is really about easing some of the barriers as we scale and as we look at combining AI and automation together. And this covers the entire cycle. First, let's talk a little bit about orchestration. This can mean a lot of different things. I've actually gotten to the point where I don't want to use the word orchestration anymore because it can mean so many different things. But this could involve workflow planning. It can involve instrument control and data analysis. So here, if we had a central orchestrator, and think orchestra in front of a choir directing how this musical program or workflow is going to continue over the course of the cycle. We have an orchestrator that could contact this autonomous laboratory, which includes our automated hardware, private data stored somewhere, as well as our experimental planner or the AI, the decision making, and being able to pass data and commands back and forth smoothly, as well as being able to integrate with external resources, public databases, or using APIs. We'll say this is where some agentic workflows could really come in handy. Maybe you automatically contact that hasanyone.com style approach there. Now, here we have a color matching self-driving lab. So this would definitely fall in the toy example. But we are performing a closed loop optimization where we have some target color, and we kind of set that in advance. We take the discrete spectrum, like use a light sensor to measure intensities at different wavelengths. And we say, okay, pretend we don't know that. All we know is the distance from what we're currently measuring, some kind of color distance from what we're currently measuring to what we're trying to get to. A distance between the two spectrum, if you will. And in this case, it's using a wireless charging base for the spectrometer. And so it goes and it picks up the tool. It's communicating over Wi-Fi. It has a small battery on board. And so for the 10 seconds that it's been lifted off of the plate, running on battery power, takes the light measurement, puts it back. And it's similar to the other Frugal Twin example. It's reusing hardware in it's reusing that same liquid handler to pick up a tool and do these tool changing, tool swapping workflows. But I wanted you to keep this workflow in mind. But before we do that, I am going to show you this workflow in action. Give me a second. Oh, sorry. Okay, let me. Yeah, I promise it's worth it. Yeah. So right now we have a YouTube live stream going to this color matching self-driving lab. This device is currently located at 700 University. So we have a camera pointed to it, 24/7 live streaming. And just as a quick tidbit, we capture YouTube gladly stores 8-hour chunks for us indefinitely. So that's just a nice little tip there. And this particular one is remotely accessible. So we're going to go here. I'm going to enter an ID, and we'll. Could somebody give me some numbers between 0 and 300? 42. Okay. Okay, 42. Next number. 70. Okay, and then one. Go with 150 here. So if we look over here, we're going to look at the queue status. It says, okay, no active experiment is running. There's no one in the queue, and we have 45 available experiments. Expected time to get the result is 2 minutes. I'm going to go ahead and go down here and click submit experiment. Did I click it? There we go. All right, so it says status running. We're going to go back to that live stream. Okay. Okay, and it is running this experiment in real time. I was once presenting this to the adaptive experimentation at Meta, some of the big wigs there, and it was just a couple of us, and it's like after this conference, and we had Eitan Bashki, and he said, no way. We're in New York at the time. It's like, there's no way you're controlling that remotely. But lo and behold, we had something like this. So this idea of cloud laboratories is something that as a community, we're far in some ways, but we're close in others. And when we get into this idea of delocalizing our experiments, it actually allows us to collaborate interdisciplinary more easily. So for this one, it takes about 2 minutes to run the full experiment. And then towards the end, so after we deposit blue, then we'll pick up the color sensor tool and get our 8-channel, sort of our 8 intensity values at different wavelengths. Now, we've used this in a number of different venues. Just recently, last week, there were a dozen or so students in Mexico that were remote accessing this machine for a self-driving lab workshop, and they ran a couple hundred experiments on this. So there, it picked up the tool, collected the data, put it back, and then we should. Another side note. After we'd run about 1,000 experiments with this for a class at U of T, the tool itself got a little chip in it, so it was no longer picking it up. So then we decided, okay, let's redesign a little bit, and we ran 4,000 cycles on it, and it did fine in terms of pickup. So that's probably good enough. So let's go back to here, and we'll see that it's changed to experiment completed, and we have our commands and the sensor data coming back to us. One thing I'd also like to mention is that this comes with a built-in application programming interface. So you can just as easily install the Gradio client, is what it's called, in a Colab notebook. For example, this is how we have most of the students that have used this interacted with it, is over a Google Colab notebook, but basically running some Python code for it. And the particular function that's exposed and gets used, I think here. Submit. So right here where we pass in our ID, this could be like an API key, as well as our red, yellow, and blue values there. And the nice thing about this is it was built in. We didn't have to design some specialized version. We just used a very common and very popular Python web application package to write the GUI, and the API came with it. And that was important because we had people asynchronously accessing it through the GUI, as well as programmatically stacking the queue together. So how do you get the programmatic usage to not step on the toes of the person using it manually? These are the kind of considerations we need to have. And to do that, if you have a user interface, you should be able to call that with Python and ideally be able to represent that web application in Python as well. That's one of the ways we can kind of reduce the barriers there. Okay, I went off on some tangents there, probably because I'm so excited about the system. Yangguang Liu did a lot here, and this has been a really nice prototyping platform for us. This was the pre-recorded video that I'll skip in case the live demo went wrong. And then I want us to think about what information would you need to capture in this color mixing experiment. So both in terms of an individual workflow, running one experiment, and then this overall campaign. Now, we won't do group discussion for this, but I'd like to just ask what are people's thoughts? What kind of information do we need to gather from here? Wavelengths, yeah. So we have all the sensor values, and we need the intensities at each of those. What else? Can you say that again? Yeah, exactly. So stock. Last week, because I'm usually not the one running these more technician level tasks, I forgot to check to make sure that the liquids were fully stocked. And they had, for one reason or another, used yellow for 300 microliters of yellow for 20 experiments in a row. And so we just blasted out the yellow. So I went in and had to restock that. How do we represent that digitally to handle these human in the loop tasks? Any other information we need to capture from here? So that could include, a timestamp for somebody, performing a workflow. Back here. Yeah. Something for this one that we found, in terms of like that metadata, the version of that housing for the spectrometer did affect our sensor values. So when it broke and we redesigned it a bit, it affected our measurements as well. So things about the state of the setup even can be really important.
Like the tip size.
Yeah, so tip size, definitely. Absolutely. So color matching, like liquid color matching, is not particularly unique. It's been used quite a bit in self-driving lab education. And the professors that will use this for their classes will sometimes change the concentration on their students for the final project. And so they build some system based on assumptions of one concentration, but it doesn't generalize to the next one. And what happens if that concentration is changing over time? So yeah, concentration of stock solution. Any other ideas? Perhaps the obvious one, what was the red, yellow, and blue mixture that we requested? The 42. I don't know if that was a reference to Hitchhiker's Guide to the Galaxy or not, but it probably was. And the 150. So yeah, the red, yellow, and blue concentrations there. Anything else before we move on? Yeah. Yeah, exactly. And so these checks in the workflow, and there are different ways you could approach that. maybe you are using the sensor measurement at each spot, and you should see a change in between sensor measurements. Maybe you're taking a background, for example. That's one thing in this workflow that's relatively important. What are the lighting conditions around the room? And having a background measurement for each experiment would be important in this case. Any others before we move on? Yeah. Absolutely. So the answer was like the state of the system. So battery charge and whether the API is communicating. As you can imagine, during the kind of last year or so for the system, we've run into plenty of times where things were disconnected. We had two distinct devices. One was a microcontroller for the spectrophotometer, the light sensor, and the other one was this OpenTrons liquid handler and the firmware and the operating system running on that. And we had both of these communicating over the cloud with each other. So they were completely distinct and separate, controlled from some high-level central orchestrator. And there were plenty of times where things stopped communicating. I say plenty, but there were actually probably only a couple times, but it took a lot to debug some of those communication issues. And one was a certificate that was expiring on the microcontroller for doing the cloud communication sort of thing. So tracking the health and the state of the system can be really important there too. Okay, in the back. Calibration, yes, absolutely. So running regular calibration. Now, for this one, is this a very well calibrated machine? No, but could somebody use this and kind of run a calibration study? I think so, and that's an important topic. So what was the timestamp of the calibration? What was the procedure that was taken in order to do said calibration? And OpenTrons has its own set of instructions for running calibration on the pipette at regular intervals. How do we capture that in the workflow as well? Okay, any others? Okay, we'll keep going. So a couple of those that you pointed out, we had the intensity values as a function of wavelength. We have things like the well position. I'm not sure anybody mentioned that one. It's kind of metadata of which well did you place this into, as well as what was our red, yellow, and blue, tracking the stock solution, the concentrations, as well as at the top right, like some of our consumables that we're using there. Now the next question is, how would you represent this information to a computer? I'd like to go through a couple examples, and then we'll come back and do some group discussion on this. So there are three common approaches to storing information in a database. We have document level, we have relational databases, we have graph databases. Document would look something like this. If you had a dictionary of key value pairs and you're just saying like, okay, I have this metadata and here's the value for it. A typical one that's used is MongoDB. People tend to say this doesn't scale well. Once you've used it for years at large companies, it becomes quite a pain, but it's also very quick and easy to get up and running. And they have a generous cloud free tier. So I tend to use it as a quick and easy document data dump for projects. And then I take those and sort of download the whole data set and process it elsewhere. We get into relational databases. For these, we can look at these. So you have tables, and then you have certain columns that correspond from one table to the next. So with this one, we have a student, and there's an ID associated with that. And then another one, you have a participants table, which then has the student ID, which corresponds to the different activities. And then you have the cost of different activities. So you see the relational piece is that between distinct tables, and think, yes, like two-dimensional tables with columns and rows, certain columns are, have information that's reused elsewhere. One of the most popular databases is called Postgres, or PostgreSQL in this case. This is probably one of the go-tos for most people building kind of larger relational database systems. And then we get into graph databases, and probably the easiest way to talk about this one is with social networking. So for example, you have Matt who posted post 1, 2, and 3, and Matt is friends with Sarah, and Matt is friends with Tom. And so now we have nodes and these edges, directional edges in some sense. And it's a little more like speaking sentences. Matt is friends with Sarah. And so this is another way to represent some of our data. And one of the popular choices for this is Neo4j. And document might be the easiest to start up, but you lose some benefits once it can be difficult to scale when you have lots of data that has lots of complex representations to it. And then graph databases are usually even more complex than the relational ones to build, but start getting into the idea of the theory of everything. You can represent anything and the relationships between them. And so you have to also be cautious not to let the pursuit of a database become the end in itself, rather than maybe kind of losing some of the science behind it. So let's jump back here. We have this data for this workflow, and how would you represent this information to a computer? Now, you don't have to say it necessarily in the database framework. You personally, what would be your go-to for representing that information? So we'll take a few minutes and discuss, and then bring it back together. Go ahead. Okay, we'll bring it back in about 30, 20, 30 seconds. Okay, so how would you represent this information to a computer? It doesn't have to be only this, but for this whole workflow, how would you represent this? In the back. Sorry, can we get the microphone?
Trying to limit, like, I mean, that is stuff.
Anyone else? Okay, so a star, you like relational, a star schema, explain what that is. What's a star schema?
Like one central table with, everything else links to the primary key of that central table and the foreign key. And yeah, just like, the result of the parameter or one table. So it seems like it's sampled at given intervals to just have 8 columns.
Okay, so 8 columns in one table with the value measurements, and then what's the relational column?
It's like
zero. So, there you go. Yeah, experiment ID.
When you request it, you put that in before you do anything else, in case it's cracking, you can repeat it.
Yeah.
So like include like a Boolean value for whether it's been done or not.
Okay. Yeah.
Like and so on. So you
Yeah.
can recover nicely and like state tracking and stuff.
Yeah. Let's say you came to the point where you wanted to add a background measurement for each experiment. How might you approach the evolving of something without a background measurement to now you need to represent, kind of distinguish between background and
So like the background, you mean like you take a blank before.
yeah, you take a blank beforehand. So it's now, how would you update that schema to,
Oh,
Yeah.
carefully. You would definitely write an integrating test suite beforehand to make sure before you update your production database, do it in a test database, and make sure your code works as you think it does for past data, and then going forward with future data.
and then in terms of labeling, maybe you had experiment ID and here's this one spectrum associated with that. Now, some ways I could think of, you could either add 8 more columns to this experiment ID, and those are background measurement columns. So you have channel 432 nanometers and then channel 432 nanometers background. Or you could do something where then you have, instead of an experiment ID or only an experiment ID, you have measurement IDs. And then those measurement IDs are attached to some experiment, maybe with a label of background or not. Like, does that kind of jive with the?
Yeah, you can totally do that. You can have, I think, rather than the same table in a separate column.
Yeah. Okay, anyone else? How would you represent this information to a machine? we have anyone here by raise of hand that's used a graph database before? A chance. Okay. Oh, sorry. Was there somebody in the back? Yeah. Okay. We'll go there first. Well, if you don't mind me putting you on the spot, one of you, how might you take this approach with a graph database? Now, granted, probably majorly overkill for just this one workflow, so you can kind of picture where it might be involved. Would you feel comfortable sharing some thoughts on? Yeah. Okay.
Yeah, I guess it does seem a bit overkill for like the simple example, but I guess where it might go is like using the graph edges to sort of traverse to where like the intensity makes sense for like which color.
Yeah. And so the kind of as a sentence, what would be like the sentence for two nodes and the relationship between them? You could think of the example. Now, I don't have a great answer to this either. I'm still learning.
I guess I wonder if it would almost be more like it's sort of like Boolean search where if like this color has this wavelength.
Yeah. Yeah, absolutely. And you know, this this mixture has this property. So maybe you have wavelength, intensity at that wavelength, and you have the particular experiment or mixture that you did. And this mixture has the property of blank. Like I've seen some of the graph database schemas and materials representations kind of have this, has the property blank that can be used for that. Anyone else before we move on? Okay, in the back, and then so.
You have like a each well be represented by a bracket by itself, but the entire say array may be a bracket itself, like graph level representations. Each person, each one of the variables. Right?
Yeah.
So it looks very daunting to us, but for the machine.
Yeah. And then there's somebody over here. Yeah.
I was thinking about, converting intensity in ratio. So if you have a calibration tool,
Yeah.
and if you have a sample where you don't know exactly let's say the ratio between the color, so you can maybe assess, the ratios.
Yeah, absolutely. Maybe this goes a bit too much in detail, but what you get from that spectrophotometer, this light sensor, are counts on this analog digital converter. Now, to go from those raw values of counts to something physical, meaningful, like irradiance, watts per meter squared, you have to do you have to do some calibration for that. And so you start then talking about ratios and, do you do background subtraction or, some kind of ratio representation for it? That makes sense. And then just piggybacking off to the well plate representation, a little bit later, we'll show an example of a human in the loop manual intervention step, a maintenance task, and how the well positions get represented. So that idea of which wells are used, which wells are available, plays a lot into that kind of information being stored. Anyone else? Okay, we'll keep going. So, human intervention. We have this experiment, you can run it in a closed loop, but what happens when you run out of wells in your well plate? This is where it's really important in the community to avoid all or nothing thinking. Oh, either is going to be completely or mostly manual or completely autonomous with nowhere in between. One of the ways that we can have a middle path between this all or not, within this all or nothing thinking is to have software drive the human in the loop workflow. And so what this looks like is we have, excuse me, human, the well plate slots are used. Please replace the well plate with a fresh one. Now we can actually see this in practice, an example here with the color matching demo. So we have this deployment called Wells Maintenance running on an orchestrator called Prefect. Now, we also have let's see. So we have here at the right, it says available wells, 2 wells. Now, it was already updated in the background to change that to 1 well, which is the trigger for this human in the loop intervention step. So we'll hit refresh queue status. It'll change from 2 wells to 1 well, which then triggers this orchestration step, which it comes in the form of a Slack message. It says, okay, please replace this. You click on the link, which takes you to an interface representing the whole workflow. And at the top right, there's a button. You click resume. Then it asks you, okay, what's your name? Like, what's the operator name? Actually, click submit. And the workflow will change from paused back to running, at which point it will trigger this wells maintenance function to run, which goes in and updates the database representation of the wells to go from used to all available. So you can see that refresh queue status, available wells 84, and then you can see the well plate maintenance task recorded here with the timestamp and the operator. So this is one example of how you can have human in the loop intervention that's software driven rather than human driven for that workflow. And one of the most powerful things about taking this approach with your human in the loop integration is that that step is a Python function. For all intents and purposes, we'll just say it's a Python function that once it is automated, you can swap it out with the automated or robotic version. So it sort of forces you to set up your system a way to make it easier to move along that spectrum to more fully autonomous. Whereas when you have the human as the orchestrator, there's so much that it's captured in the mind. Okay, I'm taking this file and moving it over here, and I just need to remember that the well plate is over here. In its simplest form, you could use a programming statement that just says, pause, wait for user input, and then you go do something and you click enter, or type in Y and click enter to resume it. In a maybe more sophisticated way, having something like Slack integration, you're allowing the software to use the tools that machines love and use, and you allow the humans to use the tools that humans love to use, like Slack, and find a way to integrate and connect those. There are 3 primary types of human intervention. The first are maintenance tasks. So you can think of these as the technician tasks. So for example, in this case, all wells are used, please swap out the plate. A second category would be error handling, and this is more like the engineer task. So for example, you expected a sample to be there, but it wasn't. Why? We don't know. We need to go back and investigate. And then we get into a third type of human intervention, which is decision making. So for example, here we have a liquid extraction happening. So you mix these things together and then you let them separate. And then you want to remove one of the separated phases of the liquid mixture. Somebody can look at that and say, should I continue this step or not? You have somebody who's been looking at these types of reactions go on for years. They have a lot of domain knowledge. They have intuition built around this decision making. Could you trigger a step that's requesting human input to help you with your kind of augmenting the AI with your domain expertise? A couple other notes. This will bridge more into tips and tricks to building your self-driving lab, common pitfalls. Talked about it. Don't underestimate the pain of manual equipment. And graphical user interfaces from vendors that don't have an API, essentially. So when you're looking to purchase equipment or you are exploring different tools, whether they're open source or closed source, ask, does it have an application programming interface, an API? And preferably one that is Python and open source. And then you can ask, please provide an in-person or virtual demo of this API and usage. It's hard to hide things when you get a video or a live demo of this. Same thing with sample transfer. Your samples have unobstructed access from the top or the side. And so please provide a recording of the sample loading and unloading process. This could save you potentially months of pain and really speed up your procurement workflows when you're working with vendors to source these kinds of equipment. And the community faces significant challenges when it comes to standardization. By way of anecdote, my favorite class that I ever took was called Theory of Predictive Modeling at Brigham Young University. And in this class, we were told you can use whatever programming language you would like. However, the TAs will help you in Python, and all the tutorials that are worked out will be in Python. Now, I was a plucky physics major at the time, and I really liked Mathematica. It's the symbolic programming language, still perhaps the best symbolic computing language there, and I find it personally fun to code in that one, and so I decided to use that. What did that mean? That meant that I was unable to help most of the other students in the class, and they were unable to help me, at least not as much. There was a severe cost that came from breaking the convention in the choice of tool. Now, Tim Peters, who authored the Zen of Python, it's a fun set of, when somebody says, this is Pythonic, oftentimes they're referring back to this Zen of Python or these kind of principles to programming the Python programming language. And he says, a universal convention supplies all of maintainability, clarity, consistency, and a foundation for good programming habits or just habits in general. What it doesn't do is insist that you follow it against your will. That's Python. And as self-driving lab technologies become more mature and widespread, the role of the researcher may start shifting towards translating results from autonomous experimentation into scientific understanding. So maybe just going back real quick on this conventions, we'll talk a little bit later about some of the resources that are available to learn what other people are doing. We can say in a pre-competitive fashion or in a sharing best practices and principles, and the Acceleration Consortium has a number of resources, these community curated and community driven resources for them. So let's talk Mario Kart for a second. Who here has played Mario Kart at one point in their life or another? Okay, most everybody here. So you pick a rider and you pick, you pick a rider and you pick the corresponding kart, and that determines on some level your skill levels for weight or speed or acceleration. And I have this question for you. Would you rather hire Mario, Bowser, or Baby Peach? In this case, neglecting, of course, child labor laws and anger management issues on your team. On the left, Mario is well-rounded, and Baby Peach has amazing handling. Bowser has the most speed out of these. So who would you choose? There's not one right answer, but this is to get at the point that when building a self-driving laboratory, a highly interdisciplinary skill set is required from physical science, robotics, computational science, data science, software development, and engineering tasks, and more, but just a few of the categories. And there needs to be someone or something to glue those interdisciplinary skill sets together. Oftentimes it can be almost like speaking a different language with each other, under the guise that you're all speaking the same, English or whatever the language may be. An effective cross-disciplinary communication requires shared vocabulary and conceptual understanding. So let's take this example of an aryl halide I'm not a chemist, by the way, but I learned what an aryl halide is, sort of. And on the right, a posterior distribution. So on the left, we have this definition. An aryl halide is an aromatic compound where one or more hydrogen atoms in the aromatic ring are replaced by halogen atoms. If you're not a chemist, oh, this would be crystal clear, right? So if it's not, let's give you a formula. And if it's still not quite clear, let's give you a visualization. On the flip side, a posterior distribution is a conditional probability that updates the prior probability with information from the likelihood via Bayes' rule. If you're still a bit fuzzy on that one, here is the equation for it. And if you're still wondering, this visualization should make it crystal clear. Now, to meet people where they're at, we might, on the left-hand side, we might need something like this for the representation of what the formula is, or a visualization like so that connects our text-based definition with our mathematical representation of it and our visual representation of it across the board. Similarly, on the right side, we can connect our text definition with our mathematical representation and our visualization to help get the point across. And this is particularly needed in these interdisciplinary teams to meet people where they're at. They are experts in their own classical training and field, but not necessarily in yours. I know it's obvious, but it is a regular problem and occurrence, so it justifies taking some time to think about it. The Acceleration Consortium has a series of micro courses. I've developed these over the last couple of years with a number of people, and these cover topics from Hello World, just building a bare bones, minimal working example of a self-driving lab, moving into deeper dives into data science topics, into robotics, and into software development. And all of those four are asynchronous. The courses in themselves are self-driving in a sense. And then the fifth and final course is more of a capstone project, in-person, synchronous in Toronto. And this one takes on the form of building an autonomous chocolatier out of a series of modules and equipment. And so it really gives this hands-on look at how you take a system with multiple components. You have a chocolate 3D printer and a robotic arm that you can choose to use to transfer it to a plate that spins with a camera and doing a 3D representation of this. And the optimization task is find the optimal print parameters for this chocolate 3D printer that gives you the best print quality where your actual printed chocolate, the shape of that matches closely to the original file that you were trying to recreate. So it's very hands-on, much more free form. Design and build your own system using some of the tools you learned from the previous courses. In the first course, I'll just briefly go through some things. You are building a self-driving lab from scratch. Now this one uses red, green, and blue LEDs, so it is color matching still. I feel particularly proud that maybe 4 years ago at this point, I thought, is there anything simpler than this liquid matching? It's probably hard to do it for just a couple $100s in a really easily reproducible way. And I thought, well, what about LEDs? So red, green, and blue, this works out pretty well. We have maybe 400 of these kits that are floating around in the wild around the world being used for educating around self-driving labs. And the crux of it, we already kind of knew this from before, but we have red, green, and blue. We adjust the power levels. Each of them have a discrete spectrum associated with it. We have our target color that we predefined. We have our measured values, and we take the difference between those. We then ask the question, what method can I use to reach the target value? And run this in a loop. So that's the gist of course one, and then we have deeper dives into specific topics for data science, robotics, and software development. So I mentioned we had a couple different resources that are these community curated resources. The first one is called Awesome Self-Driving Labs. Now, GitHub, the most popular platform for hosting code, has these awesome lists, and they're these community curated lists of software tools around a specific topic. And this is what the one for self-driving labs looks like at the moment. So you just Google awesome self-driving labs. It should be one of the first hits. We go there and we can see it's fairly popular. It's around 200 stars, if that means anything, on GitHub. But there's been, a couple dozen contributors to this list. We have series of review articles. We have articles of actual self-driving labs that kind of characterize their level of automation with the emojis. We have a list of common workflow orchestration platforms, optimization algorithms, and other methods like that. And there's some instructions there on how to contribute to this list as well. So this can be a really nice set of tools. Oh, I'm looking for an orchestration package or an optimization package. And this was tied pretty closely to a review article called Self-Driving Labs for Chemistry and Materials. So it captures a lot of that information too. The second resource is called the Accelerated Discovery Forum. So if you Google Accelerated Discovery Forum, it should be one of the first hits. And here we have a list of topics. Now, this is built on the most popular open source forum platform. It's called Discourse. So that's running under the hood, and it functions as a very normal forum. So you sign up for an account. And in this case, one of these topics that it's going through is on powder dispensing. So how are people around the world handling the topic of powder dispensing? So liquid handling, there are challenges, but it's quite a bit more straightforward than handling powders and solids in kind of an arbitrary fashion. I would argue about an order of magnitude more expensive and more difficult to manage that. So over the course of a year or so, we crowdsourced lots of different implementations of people and kind of discussion around how they're approaching that problem. So my challenge to you is to take time and read through at least 10 topics on the Accelerated Discovery Forum before the end of the week, and pick out these topics that resonate or strike with you, which covers many of the concepts that we've talked about just now about databases and designing automated systems, choice of AI algorithms, and make an account, post on there if you have something you'd like to say or participate in. And at the Acceleration Consortium, we're building 7 of these self-driving laboratories, from inorganic, often like inorganic solid state synthesis, organic small molecules, to then medicinal chemistry, a lab, the polymer lab focused on polymeric materials, also a formulations lab. So this could be like shampoos or nanomedicine formulations. And the 6th lab, SDL6, called the Human Organ Mimicry Laboratory. So the growing of cell cultures for heart cells or liver, kidney cells that can then be used for drug testing, for example. And then a 7th lab, which is primarily at University of British Columbia, which is the scale-up laboratory, really focused on going from gram scale synthesis to, kilogram scale. I'd like to close out with an analogy to fishing when we're building a self-driving lab. Could I get somebody, Larry is still around, could I get somebody to read this quote for us? With a nice loud voice, and we'll get a mic. Could somebody read it for us? Just raise a hand. Okay, up here.
None of us should be like the fisherman who thinks he's been fishing all day, when in reality he spent most of his time getting to and from the water, eating lunch, and fussing with his equipment. Fishing success is related to how long you have your line in the water, not to how long you have, or not to be how long you are away from the apartment. Some fishermen are away from home for 12 hours and have their line in the water for 10 hours. Other fishermen are away from home for 12 hours and have their line in the water for only 2 hours. This last type may wonder why they do not have the same success as others.
So what does it mean to have our line in the water as we're doing scientific research? Could I put you on the spot? Do more of it? Okay. Yeah. Any other thoughts? What does it mean? Yeah. What does it mean to have our line in the water?
Make it try instead of just overthinking.
To try things instead of overthinking? Okay, yeah. I want to, any other thoughts? Okay, in the back. We'll get the, yeah, Mike.
For in the state, like to be collecting as much data as possible when the
Thank you. So let's take a look back at those examples at the very beginning. We have the discovery of penicillin by Alexander Fleming. We have the discovery of thermal shock resistant glass by Donald Stuckey. We had Kevlar discovery during nylon studies. One common theme of those is that these people were actively researching a topic and they were actively running experiments when these serendipitous discoveries occurred. Now, one of the challenges with building a self-driving lab is that it takes a lot of work to build. You can do things to reduce that burden, but very quickly you can run into a situation where someone with classical training in one discipline spends 80 to 90% of their time learning the skills in across disciplines. So, a chemist or material scientist that needs to learn robotics and artificial intelligence. Now, having a certain level of understanding the cross-disciplinary aspects can be really important, but let's not let this keep us from doing real science. And the more that we have our lines in the water by running actual experiments, collecting actual data, the more likely, I would argue, we are to have success in our respective science disciplines. Now, your next steps are some intersection of your skills, your interests, and the opportunities afforded to you. So skills largely ties back to classical training and whatever you've taken upon yourself to learn. The interests, what excites you the most? And the opportunities, what organization or lab are you a part of? What are the existing skill sets there? Finding some combination of these allows you to determine what your next steps in building a self-driving lab and using it are. So let's finish out this session with a little bit more discussion. And you could think of this a bit like commitment brainstorming. What are your next steps that you're planning to do in order to more fully participate in the accelerated discovery movement that we're having in the world. So we'll take a few minutes, and we'll bring it back together, wrap up, and leave some time for lunch in the upcoming sessions. Go ahead and take it away. Just a couple minutes of discussion. What are your next steps? Okay, we'll bring it back together, about 20 seconds. Or sooner. Okay. Can we get just a couple of people to share? What are your next steps? What's your commitment? What are you going to do? Okay.
So I'm a final year PhD student, and I've been doing a lot of modeling, experiments, and things. And I have been thinking that it would be great to have a fully automated self-driving lab for my work, and that could have just been waiting for someone else to do it. So I think that my next steps are, using the network that I have, I think hopefully developing the meeting next and figure out how best to get involved in self-testing this. Yeah, using some of the tools that you have today to just start doing line and just by pushing.
Awesome. Thank you. Anyone else willing to share? Okay, maybe one or two more people, if you don't mind. Can be really quick. What's your next step? Okay, right here.
Currently, I'm going to be probably using the Honey Lume tool to
add Bayesian optimization into one of my projects. So that's my next current step.
Did I plant you in the audience? Thank you. Okay, one more. Okay.
Yeah, I think it is. It's never been working for a lot. If my lab is sharing it. Yeah, so sharing the work that I'm working on in a more open source way, so maybe like say here the work that's done.
Awesome. Thank you. All right. So let's use AI, maximize the value of our experiments. Let's use automation. Let's minimize the burden of it. Let's figure out ways to integrate these systems together in a way that allows our fishing line to be in the water, to do real science, and allow for both engineered and serendipitous discovery. And I'd like to close just wishing you success in your own discovery, in your own scientific research and problems. Appreciate you being here. We can take a few questions if you'd like to stick around. Okay. Yeah. Absolutely. You should talk with Karosh Darvis and Ilya Yakovitz from the Acceleration Consortium, who really hone in on the safety aspect. And I think that, maybe you could clarify.
Well, so for example, we two over there, we took off the plexiglass. My safety guy wouldn't allow us to take off the plexiglass because we expect someone's going to go into the lab and just stick their hand in it.
Yeah.
You know, the work in government. So
Yeah, absolutely. So on that one specifically, do you remember on one of those slides we had the actuator? There's a vision camera on an actuator track, so you can move the camera around. We frequently use actuators now for doors and sashes. So picture, like a fume hood sash. And so we've actually been exploring and implementing automated fume hood sashes so that we can close it when needed. So you can imagine something similar. We have furnace doors and plexiglass here. It's not necessarily always simple to automate, but some things like that could be incorporated. And I think that another piece is just related to monitoring. The more information you have to be able to monitor, the easier it is to create alerts and have human in the loop steps of, hey, we're noticing this happening. So I think, in terms of safety, though, maybe lots of dinners with the safety people at your organization might also help.
you say that actuators are cheaper than say light curtains. We were forced to buy light curtains for one system, and it's so expensive.
For a lot of those actuators, a couple $100, but then you do need to figure out how to integrate it. So that's where, the buy versus build. Do you have something, that a mechanical engineer comes in and helps you with to design the system, or do you get something? How much do light curtains run for, by the way?
I don't know. I didn't have to buy them. I just know it was a big fee.
Yeah, gotcha. So yeah, a couple $100, some of the actuators there. Yeah, exactly. So yeah, kind of fits into that buy versus build trade-off. We're thinking about it. It's an important topic, and yeah, maybe I'll integrate that into the next version of this. Okay, any other questions? Oh, set. Okay. All right. Well, thank you so much for being here, and I hope you enjoy the rest of your week at the Acceleration Consortium and the Accelerate Conference. Hey, thanks. Thank you very much. This is my name part. That's great. Thank you so much. And that's actually the Okay. I was there for. Wow. It's tougher. It's very. Yeah, that. And I was there, 2013. Vision? Yeah.
Why didn't you call me?
Just starting.
Oh, no, I'm like, oh,
Then not gonna wall. I was there with my dad, also my wife and my daughter, 2 years old. And when I went for vacation, I went to Easter. But you move around every maybe 3 to 6 months, and there's a lot of. All from the time out.
but we're all the same institute.
Okay, got that, yeah.
It's just a different campus.
Okay.
We all work here. Yeah, I have in my notes. I have my notes. Invite Sterling. No, I'm not joking. It's page 1. Invite Sterling. Where's
that's the last thing.
Oh.
So all.
Oh yeah. Share with that's great.
And feel free to.
Yeah. Right. Yeah.
Open with. You have a question? Yeah. Sure. That is get you there, but yeah, word. Yeah. Yeah, we see this one. The message for, I can't guarantee anything because they visit. Okay, yeah, definitely would be more than happy to do that. Thanks.
Or starting, I use your, oh, you
Yeah.
need it. If you need it, I have myself, I can just.
This is mine, yes.
Oh, okay.
If you do, see. So do you want to reuse any of the setup?
What's I have?
I mean, I brought a mic, I brought a camera.
Oh, that's yours.
Yeah, this is all mine.
Oh,
Unless you really wants it, but
this is, they will give me 2 microphones, but I don't know which.
this was for me to record it.
Oh, you mean this one? This
Yeah,
one.
I recorded on this laptop.
Oh,
So if you're not gonna record it, then
I'm not
okay,
recording.
then we'll take this, take all this time.
think we can turn the podium.
Yeah,
So
probably.
Yeah.
then the steps, so you can begin to that.
Yeah,
Comfortable with the hand, or do you prefer this?
I'm comfortable with whatever, but I'm not a speaker, so. But I guess we probably need